Okay, I want to start out talking about some ideas of how to think about capacitors. And here's a circuit, and we know this is a low-pass filter. Why is it a low-pass filter? Well, it's because capacitors don't like to let DC voltages go through them. AC voltages can pass through a capacitor, but DC voltages cannot. So if the signal is coming in and it's DC, it will just go on its merry way, and this can act like a filter. But if it's AC, then this will start to conduct a little bit and it will pull it to ground. So you can think of it like this. It's like a variable resistor, and the resistance is a function of the frequency, right? So at low frequencies, it's like a megohm. But at high frequencies, it can go into the ohms region, right? And you can imagine in a system, maybe this is a 50 ohm resistor, okay? And what happens where the condition of this resistor, the frequency makes this resistor 50 ohms as well? Well, then you have a voltage divider and you'll only get half of what you started out with, okay? And then it can go down to maybe 1 ohm, and then you only have 1/50th of what you started out with, right? So I think everybody understands this, okay? We can plot it, okay? And so, you know, it would look something like this, okay? All right, well, let's just think about another case. Where we have now an inductor, okay? But it's the same thing. The resistance is going to be a function of the frequency, okay? So inductors are very good at passing DC voltages, but AC voltages get blocked because of all of the magnetic flux and stuff. So in this particular case, the high frequency will go through, but then the low frequencies will start to get cut off, right? So you can end up with something like this, where at DC, so this is frequency and this is amplitude, let's say, okay? So at DC, this thing's going to look like a short to ground, okay? It'll look like a short to ground. Let's say this is 50 ohms again. So at DC, this might be 1 ohm. And whoop, you get 1/50th the amount. But at a megahertz, maybe this is 1 megohm, okay? And then you'll get to have just as much out as you started with. And so it'll do this type of thing, okay? Well, what if you had something that had both an inductor and a capacitor, okay? Well, you end up with something that looks like this. It kind of dips down and then it comes back up again, okay? So that's the way to think of it. It's like a variable resistor whose resistance is a function of frequency. If you have two things together, you can do things like that, okay? But let's talk about one device. Let's talk about this capacitor. People have seen me, I've got a reel of these. This is a 0.01 microfarad capacitor. And capacitors are not perfect, okay? So let me show you a paper that I found. It's a really good paper, quite readable. Where did I put it? So here's a paper, how to measure capacitors using a VNA, a vector network analyzer. And they draw a nice picture here that a capacitor actually has capacitance. It has some inductance because it has leads, right? It has the length of wire, so it has some inductance. It has some series resistance. And then there may be some leakage across the capacitor, so there may be some resistance across the capacitor as well. So a real capacitor has all of that stuff in it, okay? When people do capacitor models, they generally model it this way, that there's an inductor, a resistor, and a capacitor. But it's actually a little more complicated than that in the real world, but this is what we're thinking about, okay? And so here he gives a nice graph, should look very familiar with the graph I just drew, where when the capacitor is doing its job, it's falling like this, and then because we have both, that little bit of inductance will start to work at super high frequencies, and you'll start to get this again, right? So the capacitor's trying to do its job, but then the inductor gets in the way, right? So one of them is dominant. Either the capacitance is dominant or the inductance is dominant, okay? So he goes on to talk about a whole bunch of other things, and I sort of was thinking about doing a video like this, but what I sort of got sidetracked on is a different topic. So I'm going to do that different topic first. And what I'm going to talk about is something that I've known about, and I have sort of seat of the pants used, but I've never really measured it before, and I don't know why. That is, if we have a system where we have frequency and amplitude, and we're trying to, you can call it a bypassing capacitor, decoupling capacitor. You want to remove the noise in a system. That's why you add capacitors, is to reject some of that noise, and you want to basically shunt that noise to ground. And that's a lot like those pictures I just showed you. You want to have whatever frequency that you don't want to be attenuated, okay? And so you put in a capacitor to ground. And you would hope that your capacitor to ground does this, right? And so whatever frequency you're interested in, it gets attenuated. Now, when you're starting out, you might think that, oh, then it just continues. That if your capacitor is able to kill 1 megahertz, it will certainly kill 10 megahertz and 100 megahertz. You know, capacitors will conduct higher frequencies. And so you're kind of taught that this thing goes down and then just stays down. But we've just seen that the inherent inductance that's also part of the capacitor will make it do this. And now, these frequencies out here that you hope that you're killing are no longer killed. They go right through the system. So you say, oh dear, I need to choose a different capacitor. So you might choose a capacitor that has its dip over here. But then this one gets through. And you say, well, I want to kill all of those things. So there is let's say this is ground, and here's your signal, and you put in a capacitor, a decoupling capacitor, and maybe it's a 0.1 capacitor, and then you say, oh, I'm going to put in another one. I'm going to put in a 0.01 capacitor. Oh, I'm going to put in another one. I'm going to put in a 0.001. And oh, I'm going to put in a bulk capacitor too. I'm going to put in a 200 microfarads. I'm going to have all of these capacitors all together. And I think you may have seen people talk about these. Dave over at EEV blog did a very long video on all of this type of stuff. But like I said, I've known about this, I've used this, but I've never measured this. So let's go ahead and measure this, because I think it would be fun and instructive. All right, so how should we measure this curve? Well, I have 2 instruments that I could measure it with. One is a spectrum analyzer with a tracking generator, and that could measure this. And one is a vector network analyzer, S21. Okay, that's a scattering parameter of output of port 2, input of port 1. Anyway, it's the through transmission of a system. All right, so let's go ahead and do that. Okay, so before we can measure our capacitor, we need to have a fixture. Okay, what's called a fixture. And I have designed and built my own fixture. And it is going to be 2 coax connectors on a ground plane. And there's going to be a wire that goes across. So that's going to be my signal wire, okay? And then if I want to add capacitance, I can put it between my signal line and ground, okay? And so the first thing we need to do is calibrate our system. So let's do that. All right, so when you make a measurement, you can either make a transmission measurement or a reflection measurement, which are S11 or S21, okay? We're going to be using S21, okay? And we're having set up in log mag, so log of the magnitude. And we need to calibrate this, which is a measurement from this connector to that connector. Okay, it's a through measurement, but we want to do a good calibration. So on this instrument, we will hit cal. Make sure our cal kit is that one. Now this one can do a response curve, which is just a through measurement. It can do a response and an isolation, which is a through measurement and a nothing measurement, or it can do an enhanced response, which is a full S parameter port calibration. So let's go ahead and do the fancy one since we're here. It's going to ask us to put in a standard open on our reflection port. Okay. Okay, so what is a reflection port? Well, this is the reflection port. This measures S11. We're going to be measuring things at the end of a cable, so we need to calibrate at the end of the cable. So I'm going to use my cal standard, and I'm going to cal right here at the end, okay? So that's the open. And we will do the short. I'm caling between 1 megahertz and 200 megahertz, and that's just for convenience. It makes the graphs look nicer, so we'll go up to 200 megahertz. And we'll do a load. Okay, now it says we want to do a through measurement. So now we can be okay, or we can be very accurate, okay? So if we want to be okay, we would take these 2 cables that connect the input and the output. We would put a female-female adapter in here, and then we would calibrate that, and that would give us a through, okay? But our test subject is going to be using this fixture. So we're going to calibrate this fixture. First, we're going to put in a version of the fixture that does not have any capacitor on it. It just has the transmission line and the ground plane, okay? So we're going to put that in series, and we will measure that, and now we will have a perfect calibration. All right. Now, when we put in our unknown, all right, so let me show you that. If I can zoom, can I zoom down a little bit? I think I can. Yeah, so this is going to be our device to measure, and it is just a 0.01 capacitor to ground. I don't know if that photographs well, but anyway, it's a 0.1 microfarad capacitor to ground. So we will insert that in our measurements here. Okay. And there we go. We're getting that curve. It's dipping down, then coming back up again. And it's dipping down right where I have marker 2. Let's see here, marker 2, yeah, marker 2. So marker 2 is dipping right at about 40 megahertz, all right? And then it comes back up again. So our capacitor is working great down at this frequency, and then it goes up again, all right? So that's good, but maybe 40 megahertz is is pretty high, right? Maybe we want to be attenuating a signal much lower than that, right? Maybe at 10 megahertz or something. And we would, instead of using a 0.01 capacitor, let's put in a 0.1, okay? So let's do that next. I'll have to desolder the 0.01 and we'll solder in a 0.1. So let's wait for that. All right, I've put in a 0.1 microfarad, and you can see that the resonant frequency, it's called self-resonant because it has its own L and its own C. It's all self-contained, so it's self-resonant at a particular frequency. And this time, we will set another marker. This time it's resonant at about 8.33 megahertz. That's good. Remember, we wanted something maybe around 10 megahertz, right? So here, right here at 10 megahertz, it's still doing a really good job. So that's a good one for 10 megahertz. But we lost our 40 megahertz version. Well, what if we put both in? All right, that's kind of where we're leading up to. Is let me go ahead and solder in the 0.01. So we will have both in the circuit. All right, and there you go. Now we have a place here at 10 megahertz and a place here at 40 megahertz. And it's kind of squeaking up again. Let's put a marker there. Let's do marker 3. So it's not doing as good a job at 20 megahertz, but it's pretty good at 10 and 40. Maybe you would choose a different capacitor right there if you really needed that one. But I think the combination together is better than each one individually, right? And so this is kind of the idea. This is something I've never measured before. I've never played with this graph. I've seen a bunch of them online, but I've never measured it myself. So yeah, there you go. All right, here was the 0.1 microfarad capacitor that I was using. I've got I've got quite a few of these. I don't remember where I got these from, but I have several thousand, 10,000, I don't know, a lot of them. I have a whole big bag of these guys. And they are, let's see if I can zoom down here. They are glass leaded. They're clear glass. And the reason I want to talk about these is we've seen the effect of the inductance in this problem. We have a capacitor plus the leads and everything add inductance, right? So how are these constructed? Well, there's a little plate in there and there's a little chip capacitor kind of put in there and it's all bonded together, but it adds inductance, right? Well, what if we get rid of all the leads and we just use one of these SMD parts? So these are exactly the same part electrically. They're both specified as 0.1 microfarads, 50 volts, and they're Z5U. So they're both, I think they're both exactly the same specifications. It's just this one is a 1206 package, I think. Maybe it's a 1210 package. Anyway, I'm going to take our little fixture and take this and measure it, and then I will solder in this and measure it, and we'll see if there's a big difference between those two or not. All right, so here is the clear leaded package, the axial leaded package, and you can see here we're dipping here, marker 1. Marker 1 is at 8.5 megahertz, all right? So let's then turn on, I have that saved in memory. I will put in the, this is the surface mount package. You can see that I have marker 2 there. So marker 2 is at 21 megahertz. So this one was 8.5, this is 21 megahertz. So the capacitor gets to operate farther until the inductor starts kicking in. So because there's not as much inductance, the capacitor gets to do its job for a longer period of time before the inductance becomes the dominant one. And in fact, there's not much there, so it doesn't come up as fast either. It stays low. So using surface mount bypass caps is much better than the old leaded ones. So Yeah, there. So let's take a look at both of them at the same time. Data, and memory. That one. There you go. So there's both together. You can see there's a huge difference there. We get this extended frequency response, plus even out at higher frequencies, there's not much inductance there, so it stays low. So, yep, surface mount's the way to go.